Then we'll start. Well, welcome everybody. Let me start off by saying that we're really glad to be here and I'm enjoying the day so far very much. I heard a lot of great talks and I think it's great what we're doing here. I really believe that through sharing software and knowledge together, that's a really essential part in the challenges we're facing in the energy transition. Well, with all this great thinking power, building data-driven applications, I think we can do great things together. And I want to start off a little bit by asking you in the room what your background is. So I want to, by show of hands, see a little bit about which people we have here. So we're going to talk about load flow calculations and modeling the energy grid. So for the people here in the audience, how many people of you have worked with energy grid, modeling them, doing load flow calculations? So I see some hands. So if we talk about load flows, and sometimes we try to give really simple examples, but sometimes it will be a little bit more in depth, but we'll keep interesting for all, I hope. So let's start with where this journey started and the story for today. It actually started 5 years ago when Thijs and I were working at a project at Alliander. And in this project we are simulating the energy grid. So we are trying to see what effects we can expect for the coming 40 years on the grid. And to do this, we were developing a Python library which can model that. But over time, we were switching teams, so we worked in other teams. But we thought, well, the things we were building then, they would really be useful in this team as well. So we started sharing some code within Alliander in the source. And over time, other teams came along and they thought, oh, that's pretty cool, we want to use that as well. So we started maturing the software. And that's how we built like an inner source library for modeling the energy grid. And then 5 years later, we're standing here, and this project has now become quite some bigger thing, at least in our eyes. And we're launching it today officially, talking for the first time about it in this setting. As thank you. As an addition to the Power Grid Model suite, so that's already a project within LF Energy, and we're adding a new package focused on data science applications, and that's what we're going to talk about today, show some examples and show some applications we're using it for. So let me start off by the base, and that's the Power Grid Model. So give a little bit of background about that, because that's really an important part of what we're doing. It's a really high-performing load flow engine developed in C++, which we use to model loads on a network. We are not developing the core of the Power Grid Model, so don't ask too difficult questions about physics, but we're using it. So we are involved in data science projects, which really depend on having such a fast engine. So we have learned over time how that can be used in different data science applications and what additions were needed, and we're now adding to that software. So what are we doing in that? So this is a really simple simplification of an energy grid, but in the basis it's what we are modeling. And that's how energy is going through the electricity network. And we work at Alliander, so we are working at a distribution system operator, and we want to manage this grid on the short term, on the long term, and make sure that it stays within bounds. Everybody stays happy and keeps connected to the electricity grid. And that means we're modeling how this network is evolving, and we'll simplify a lot in this talk. So we'll talk about how nodes and lines are connecting components in this grid, and we want to see whether they will be overloaded in the future, short term or long term. What happens when, for example, lines get overloaded, they heat up, they become less efficient, which is of course not good in the first sense, but in the end they will also break if they get overloaded. When we put too much energy through the grid, also the voltages for customers, they get out of bounds, so they are become dysfunctional. As data scientists at Alliander and software engineers at Alliander, we continuously developing applications which try to manage this for the organization. So that means, for example, looking on the short term. So we are forecasting the next 24 or 48 hours on the network, and for example, using things like we saw before about solar forecasts for the short term, and see what will happen to the energy grid tomorrow, and have ways to manage that if we expect overloads, put in tenders on the short-term electricity market, for example, to prevent that. And we do that by simulating. So simulations will be the key of what we're doing. So we do a lot of simulations daily, in which we go through all different scenarios on the electricity grid and make changes to that grid. So if you look a little bit more into the future, then we're also working on how can we manage maintenance on the network or outages on the network. So when things in the network fail, we need to go through all the different combinations of how we would be able to solve like an outage in the network to keep everybody connected. And again, that takes a lot of simulations, interfacing with the network, changing the network, and seeing what would be the impact. And then the situation as it is today is that we have a lot of new customers or existing customers who want to use more electricity, and that frankly puts a big stress on our network, and we're not always able to manage that yet. So we're continuously looking to find solutions, flexibility in the grid to keep those customers still being able to be connected, and making forecasts on how likely it, for example, will be that a solar farm needs to be disconnected for a couple of hours in the year, and simulating on a large scale with that as well, live in tooling for people at Alliander who are responsible for that. And then last but not least, because that's what Thijs is doing at his team, but also I saw the talk of RTA earlier. We're looking like the energy scenarios for 2050, 2060, and simulating like 40 years in the future. So you can imagine if we want to calculate all those scenarios, well, we have a very powerful load flow engine which is able to do that, and now we're adding the interfacing options to that as well. So we're going to go a little bit more into the nitty-gritty, to the details of how this load flow works, and then we're going to show how the package does this. So in the essence, this is what the Power Grid model interface looks like. So this is a JSON interface towards with arrays towards the load flow, which gives you output also in an array manner, and this is what already was available in the Power Grid model. And what we now build is a wrapper to really easily interact with this and to ask questions which are from a data science sense very interesting about this. So we want to ask questions about how this network is connected, which parts of it can be filtered out, are interesting, is it overloaded, and what if we change something. So those are the things we're focusing on with this package. And we would summarize that as preparation of the network, interpretation of the outputs, and simulating that to close the loop. So I'm going to go a little bit faster because I want to give some time also to Thijs. So it's, in essence, this is the summary. It's a Python wrapper, which doesn't add a lot of dependencies. So it takes the Power Grid model, adds numpy as managing the the grid output. And we also added RustWorks to simulate the graph of the network. And with that, I want to give it over to my colleague to show you how that works and look like.
Yes. Thank you. I'll just hold it. So yeah, just to get into the more technical part of our application, just to get back to what we were simulating, nodes, lines, and transformers. You can represent them in what we do in two ways, either as a graph, which is quite natural, I guess, or as arrays, what we were already doing in the power grid model, and both can answer different questions. So the arrays you can use mainly for the load flow questions or specific properties of specific assets in the network, and the graph is mainly used for asking questions like connection topology questions. And that, as Jaap just said, for one we use RustWorks, which is a variant of Network X, for those familiar with it, and the other one uses numpy structured arrays, which was already present in the power grid model. So back to the questions, like the graph questions like these can be easily asked from a graph. So we have methods like these in our package to find out which node is connected to another node. So, for example, the first node is connected to the fourth node, but it's not connected to the 10th node. Or if you ask a question like, what are the components within this network? This is one component on the left side, and the 10, 11, 12 nodes is another component. And these can be very useful in our data science applications. And then on the other hand, we have the array questions. So power flow analysis or state estimation. We build an interface to the power grid model application that was already there. And so it's easy to interact with it, and it will update the results from the power flow into the data science application that you're developing. Made it a little bit more easier in our opinion. And another option, other features we added are filtering values. So the goal here is really to make the life of the data scientist a bit more easier. So the power grid model is really as a calculation core, and we are trying to make the experience for the data scientist a bit easier. So we added things like filtering, updating values, and inheritance of D types, data types. So for example, there's a line array on the right there, but you can add custom fields to the array or defaults, or you can even create your own complete custom array. But it's all under the hood. It's still numpy arrays, so those that won't affect performance, for example. And then one question you might have is like, how do you manage both representations at the same time? So that's also something that we added. We summarized them, or we combined them both in one grid object, and then we added functions to that object to manage both representations. So there's a graphs attribute which contains the graph, the RustWorks graph, and then these are all below that there are all the arrays. And whenever a node is added, it's both added to the graph, for example, and also added to the node array, and the same goes for branches or activating or deactivating branches. So that makes it easier to also make a dynamic grid and simulate dynamic grid, add nodes to the grid, delete nodes to the grid, and then see what that does for load flows and stuff like that. That's basically our application. We hope we can find new people to join us in managing these, building these applications and contribute. So thank you for joining us and listening to our talk.
There's time for questions.
Yes.
Yes.
Does the power grid model only take nodes and vertices into account? Or can you also, if you have like smart meter data from consumers, can you use that to inform the model?
So I think that's part of. Oh yeah.
Repeat the question.
Oh yeah. So the question, I think if I summarize correctly, is can we also use measured data in the network to inform the network? That revolves a little bit more about the calculation core, so it has different parts. So one part is the load flow engine, which is doing the physical calculations of the load flow, but it also has a state estimation part in which you can input measurements and give them probabilities. So it's more like a statistical calculation, and that's where we use it as well with measurements of all points in the network. Yep.
Do you use your graphs to make dynamic simulations, as in the course of the simulation you can change the structure of the grid, or do you have to stop your simulation, change it, and then start a new simulation?
No, we actually do dynamic simulation. So what we're for example, in my project doing is simulating 10 years ahead, and during runtime we simulate adding new clients to the grid. So that will build new lines, new nodes, and then we do a new load flow. It will sometimes cause congestion. Then we have to replace lines with thicker lines or stuff like that. So during runtime we're changing the grid, updating it, and then seeing the results. Any other questions? Yes.
How long does it take you to run one simulation?
How long does it take us to run a simulation? I think it depends entirely on what you build in your own simulation. So we are doing, in my project, we're simulating a lot of the work that Alejandro is doing. So all kinds of congestion management strategies and all kinds of ways of adding clients. So that's, we simulate 10 years in about 5 hours or something like that. This now.
The reason I'm asking is one question that DSOs often get now is from operators, where can we put EV chargers? They take a lot of power and so on. And these operators would like an answer within as quickly as possible, right? Because they're trying to plan and so on.
Yeah, so I'm not really sure I can repeat the question, but to answer the question, at least the power grid model core calculating is really designed for performance. So it's really fast, quick in calculating all these things through. So it's entirely possible to I think get a quick answer, but you have to build the simulation yourself.
So for a low voltage grid, you mean? Yeah. Yeah, so we are using it also in low voltage, so it's focused on low and medium voltage. So for us as a distributor.
Like if I want to use your project to model somewhere in the UK, I need to find that UK network and put it.
Yeah, so what we are, so the question is there a specific Dutch network modeled in this or not? So what you should see this as like a general definition of how a network can be modeled. And we internally at Alejandro are of course modeling our network, but you can model every network you want in this, whether it's low voltage, medium voltage.
Alejandro data is not included in the project.
And maybe also to add on the question about performance. So of course it depends on the use case. So I talked about some strategic use cases. For example, Thijs is one where the speed is mainly a cost concern, but it's also used in operational, where of course speed is much more of the essence. Yeah.
How badly will it go wrong if you use incomplete data? So we can get quite a lot of grid there out of FOSDEM, but it's not complete by a large margin. Just wondering, is that completely useless, or will that in fact give me any useful numbers?
And what kind of incomplete data do you mean?
StreetMap has like a fair amount of the grid, but not all of it. And there's bits, gaps and things where people aren't quite sure yet.
Okay. So the question is how does the model handle incomplete data? And I find it a little bit of a difficult question, but I'm going to try to answer. So I think on one sense, for the physical modeling, of course, it handles the data as it is presented, and it has the Power Grid model has some validation options to make sure that it's at least valid for the calculation. And then when whatever you put in, it will work with. But for example, we also have projects where we don't exactly know everything of the data. For example, switching options in the network we're not quite sure of, and then we actually use like the state estimation we were talking about, which can handle uncertainty in a better way, or we can simulate, for example, the different options and see which is most likely. So there's different ways of handling it, yeah, but it depends on what kind of data is missing, I think. Time's up.
Time's up.
Thank you.
Thank you.